Good morning everyone. I hope I am audible to you and my computer screen is properly visible to you. I want your responses so that I can continue my class. Yes, one student has replied, yes sir, you are audible and visible. So today we are about to discuss some competitive exam problems related to module number 4, that is Turing machine. We first of all need to understand the point that Turing machine is basically a logical machine. The practical implementation of the Turing machine is our computer. Turing machine accepts recursive enumerable languages. Turing machine accepts recursive enumerable languages, and Turing machine is generated from the phrase construct grammar or phrase structure grammar. Okay. So before moving into the detailed discussions about some problems which has already come in the previous previous competitive exams, let us discuss first the brief of the Turing machine so that it will be clear to you. First of all, what is Turing machine? If we go to the introduction of the Turing machine, then we can able to say that just as in physics, no particle speed cannot be greater than the light. Similarly, no computer powers is greater than the Turing machine. So, Turing machine is a mathematical model of computation that defines abstract computer, was invented in 1936 by Alan Turing. So, Professor Alan Turing discovered the Turing machine concept. It is not a practical concept, it is a theoretical concept, but or logical concept or mathematical concept. So, but it has been proved over the years that if an algorithm or a real life problem be solved by Turing machine, then it can also be solvable by the computer. And if a real life problem is not solvable or not recognized by the Turing machine, then it cannot be solved by the computer, or we cannot able to write any algorithm for solving that problem with the help of computer. So Turing machine has the same power as computer does. Turing machine is very powerful than all the logical machines. Rest of the logical machines are finite automata, deterministic, non-deterministic, push down automata, deterministic, non-deterministic, lower bound automata. We know that finite automata finite automata accepts the regular language, and regular language is generated from the regular grammar. We know that the context free grammar, which is the higher version of it, is going to generate the context free language, and the context free language is recognized by the push down automata, be deterministic or non-deterministic. Next, lower bound automata. Lower bound automata is a logical or theoretical machine. It will accept basically the context sensitive language. Context sensitive language is generated from the context sensitive grammar. Next is Turing machine. Phase structure grammar generate the recursive enumerable language, and recursive enumerable language generates is recognized by the Turing machine. There are lots of variants of Turing machines, most probably 7 variants of Turing machines are there. In due time we shall discuss that. If a task or problem can be solved using Turing machine, then our computer can also solve it. That is the main essence of Turing machines. That is the main essence of explaining Turing machine. That's why Turing machine is so important. If a problem is not solvable in the Turing machine, problem means real life problem is not solvable by the Turing machine, then it also cannot be solvable by the Turing machine. And it has been practically observed that some of the problems which are not solvable by the Turing machines are not solvable by the computer, and all the problems which are solvable by Turing machines are solved by the computer. Now Turing machine is a language generator. Acceptor and transducer. So why Turing machine is a language generator? I have already said earlier in the previous semester. Any language can be accepted by Turing machine. That is the number 1 point. Next is why generator? Like Milli machine, more machine, Turing machine can generate language. That's why it's a language generator. Milli machine and more machine can be able to generate the language. Okay. Finite automata with output. Okay. There are 2 types of finite automata with output and finite automata without output. Finite automata without output are basically deterministic finite automata, non-deterministic finite automata. But finite automata with output are Milli and more machine. I hope that you remember these points, recapitulate these points. Next is transducer. Why Turing machine can act as a transducer? What transducer does is that it can solve any mathematical functions such as arithmetic operation, subtraction, division, modulo, multiplication. So these kind of operations can be done by the transducers. So same operations can also be possible with the help of the Turing machine. Next is the definition of the Turing machine. Definition of the Turing machine says that the Turing machine, capital M, is represented by 7 tuples. First tuple is capital sigma. Capital sigma is the set of all input alphabets. Example. For example, you are observing that this is my language L is equal to a to the power n, b to the power n, where n greater than equal to 1. So you are observing that. Okay. So you are observing this language, and for this language we have 2 types of characters. One is A and one is B. So A and B are my input alphabets. So what is my big sigma? My big sigma is small a and small b. So I think I made myself very clear. Next is capital Q. Point number 2, tuple 2, point capital Q, set of finite set of states, set of all finite state of states. If you consider this particular problem, you can observe that Q0, Q1, Q2, Q3, Qf. So there are 5 states. So that means capital Q is equal to Q0, Q1, Q2, Q3, Qf. There are 5 steps, okay, in this particular problem. I hope up to this it is clear to you. I hope that. I hope that I am audible and properly visible to you. Next, tuple number 3, Q0. Q0 is the initial state which belongs to capital Q. You are observing in this following problem that Q0 is initial state indicated by the single arrow. We need to understand that there may be lots of states, but there is only one and only one initial state, which is here Q0. Okay, so Q0 is our initial state from where we are going to start our operation. What is the name of this particular diagram? The name of this particular diagram is transition diagram. Transition diagram. Next is capital F. Capital F, tuple 4, capital F, set of final state. Set of final state, where final state is a subset of capital Q. Okay, now set of all final state, we are observing that in this particular block diagram, capital Q suffix F is basically my final state, where Q suffix X is indicated by doubly circular arrow, and this doubly circular arrow is denoting the set of final states. Set of final state. This doubly circular arrow is denoting set of final state. There is only one final state. There is only one final state, not more than one. But it is possible that all the states may be final state, or more than one state may be final state. So it is very important to understand this point. Next is tuple number 5. Tuple number 5 is big gamma. Big gamma, this is the signature of big gamma. This is the Greek alphabet. So it is the tape alphabet. What is tape? What is tape? If we observe the Turing machine model, we can observe that there exists a tape. We can observe that there is a tape, and this particular tape having some tape alphabet, capital B, small b, small b, small a, capital B, capital B. So capital B is basically my blank symbol, and small b is basically the characters. Capital B represent the blank alphabet. So how many alphabets that we have in this particular tape? The answer is 6. 2 blank alphabet before starting of the string, and 2 blank alphabet I have given after the ending of the string. And my original string is actually of length 4, which is double B double A. Okay, double B double A. We are reading all this alphabet one by one with the help of the read and write head, and it has been read by the finite control unit, which is working just the same operation as the control unit. I am just discussing or recapitulating this theory once over and over again, so that we will find very easy while solving the problem. Okay, so capital B is a blank alphabet, just like in a C program. Whenever we stop a string, okay, we are ending the string with the null character. Null character denotes that's the end of the string. In the same way, the blank alphabet or blank symbol is indicating which belongs to the tape alphabet set. It denotes that the end of the string. Okay, so before starting a string, if there is a blank alphabet, it denotes that that before that small b there will be no portion of that string, and after this small a there is a blank alphabet. It denotes that after this small a there is a no portion of that string. So this is as simple as that. Okay, whenever Turing machine reads the blank alphabet, we need to understand that yes, we have already scanned all the characters. There is no more characters need to be scanned. Okay, so now we come to delta. What is small delta? Small delta is basically the transition function. At a state q0, if I read a character small a, then what I can do? I can able to move to the next another state. So from present state I am moving to the next state, and I will replace this character which I have read from the tape and by some other character. For example, suppose I have read small a from the tape and I am going to replace it by capital X, and either my read and write head either can move towards left or move towards right. This is not possible in case of the PDA, because the PDA will move only towards the left. PDA cannot move towards right or left. Both directional move, multi-directional move is not possible with the help of the PDA. So unlike PDA, so this is very important, unlike PDA, Turing machine does not use any stack. Turing machine does not have any stack, but the because the transition function definition is this. So it becomes too complex, because we need to read the current state or the present state and the current input symbol from the tape, and that belongs to the big sigma, and the current stack symbol from the tape of the top of the stack, which belongs to the big gamma. So this is very important. Unlike the finite automata of PDA, here we do not have any read or write head, because we are using the reading, we are not basically, we do not have any read head, we do not have any read head, rather than we have read and write head. That means that particular pointer which I am talking about, this particular pointer is not only able to read the data from the tape, but also it can able to write the data in the tape. That's why no stack is required. In case of the PDA, there is only one stack. But if there is a two or more number of stacks, then the PDA may work as a Turing machine. Okay, because I shall explain it while explaining another problem later on in this class. Okay, so my point is that, please note it down. If a PDA has only one stack, that is why PDA power and Turing machine power is not same. But we are observing that in case of the finite control, in case of the Turing machine, as because our read write head can move in both direction and any point of time, and it can able to read the data from tape, and it can able to write the data from tape. So I can imagine that this tape is my infinite stack. I can able to store infinite input symbol into it, and I can able to write input symbol into this it. So it is basically a stack. Okay, so basically a huge amount of stacks. So that is why if a PDA has more than two stack, where it can able to then it can able to some extent it can able to act as a Turing machine. Now let's talk about the transition function. So you are observing that at the present state Q0, which is basically the initial symbol that belongs to capital Q, by reading input symbol small a, we are reading the input symbol small a, because you see in the tape A, B, 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 there is a, so our first symbol is a small a, so we are going to read that particular symbol small a, and that belongs to big sigma, and we are going to write that position by capital X. So this A is going to be overwritten by capital X, as because this is a read as also write head. So this A will be overwritten by this capital X, which belongs to the big gamma, and we are moving our read write head towards right. So we are moving our read write head towards right. Okay, what we are basically doing here, we are basically checking in this Turing machine that whether the number of A and the number of B are equal or not. Because you see A to the power n, B to the power n, so the number of A and the number of B must need to be same. And if it is, then I can say then it is, if this particular string is accepted by the Turing machine, so I can say that A to the power infinity, B to the power infinity can also be accepted. Okay, then A to the power 1, B to the power 1 can also be accepted. I can also claim that. So that means A to the power n, B to the power n is recognizable by this transition diagram of the Turing machine. That's why we are checking that. So for every A we are checking whether there exists a B. Okay, so first A we are checking whether there exists a B. For second A we are checking whether there exists a B. For third A we are checking there exists a B. Whenever we observe there is no more A is left to be checked whether there exists a similar B present in the tape or not, then we scan the blank symbol, and whenever we scan the blank symbol we understand yes, this is the end of the string, and the end of the string means we are going to stop it. We are going to stop and we are going to move to the final state. That means yes, it is accepted by the Turing machine. So you can able to see that this is basically my transition function. At a state q0 I give small a and I move to q1 state, and I replace this small a by capital X, and I move my reading write head position towards right. So in this way all the transition functions has been written, and ultimately we observe that at a state q3 whenever I read blank symbol I replaced it by blank symbol and I move towards right, and I find that there is no more character of the string is present to be scanned anymore. So I understand yes, or there exists similar A, there is same number of A and same number of B present in the Turing machine, and so we reach to the final state, that is QF. So QF is our final state or next state, and we are basically replacing this blank symbol by blank symbol, and we are moving our read write head towards right. So I think I made myself very clear, very clear. Okay, now what about the language of the Turing machine? Whatever the language of the Turing machine, if you talk about the language of the Turing machine, then I can say these words to you, that we need to understand this point, that there is a Turing machine for a language which accepts every string, otherwise not. Okay, so if there is a language, we know that language is nothing but a collection of string, and the string is nothing but the collection of characters or alphabets. Okay, so alphabets, when they combine they form string or word. When the word or string they combine they form the language. And when the language is there, when the language is basically there, this particular when the language is basically so we need to understand this point is that a language is accepted by the Turing machine if and only if all of his words or all of his string are accepted by the Turing machine. That type of language which is recognizable by the Turing machine, which is accepted by the Turing machine, is known as recursive enumerable language. Okay, there is a subset of recursive enumerable language which is known as recursive language. In case of the recursive language, not all the words, not all what we can say that there is a Turing machine for a language which halts on every string. So that is basically a recursive language. I repeat, if I produce a language, say L, and that contains n number of strings, and for every strings the Turing machine, when Turing machine parses the string, Turing machine halts, then I can conclude yes, that particular language is basically a recursive language. Recursive language is nothing but a subset of recursive enumerable language. From which grammar recursive language is generated to? From the Turing machine is going to recognize a grammar which is known as phase structure grammar. So phase structure grammar is the grammar which generates recursive enumerable language, and recursive enumerable language is recognizable by the Turing machine. So we come to Church-Turing hypothesis now, which says that a function can be computed by an algorithm if and only if it can be computed by the Turing machine. I repeat, a function can be computed by an algorithm. That means a real life problem can be computed by an algorithm, implemented by a computer, by simulated by a general purpose computer, if and only if it is accepted by the Turing machine. This is basically the Church-Turing hypothesis. There is no practical proof of that, but it has been proved. There is no method, it is basically hypothesis because nobody has claimed that this hypothesis is wrong. over the years, has been proved that whatever be the real life problem established by the mathematician over the world, all the problems which are solvable by the Turing machine. And if the Turing machine solve it, then computer also solve it, and if the Turing machine doesn't able to solve it, then computer does not able to solve it. Now come to the halting problem. So come to the problem related to halts. When Turing machine will halt? Turing machine may halt for there are three conditions that may appear regarding the Turing machine halting condition. First condition is that Turing machine may halt. That means suppose it is scanning say AAA, so that means it is scanning say AAA BB. Suddenly, so when AAA BBB that is accepted properly, there is no more string to be accepted, then I can say the Turing machine stops its operation and it will reach to the final state. That means it will halt and reject the input. That means Turing machine suddenly stopped at the immediate point or at a immediate state. It not reach to the final state and it will reject the input. It may also happens. For example, suppose Turing machine has to, in the input tape there is a double A double B. So by mistake it has read some other character. In case of A, it has been read B. So it naturally the Turing machine then automatically halts and automatically stops at the middle and reject the input. That is also possible. And never halts and loop. It is possible, it is observable in our real life also. Suppose we have write an infinite loop in a C program and we have run it in our C software, say Dev C++, and we have observed that our computer screen is continuously printing the data. So I can say that the Turing machine is continuously moving towards Turing machine is continuously moving in between the intermediate and the initial states. It has not gone to the final state. So that the Turing machine is continuously looping itself and it basically halts, never going to be halt. So this is a practical implementation of the Turing machine when of the third case, that when Turing machine will never halt or never loop. So never halt or loop. Okay, so infinite cases, infinite loop you may use the infinite for loop or infinite while loop you may use. Okay, so you can use that for implementing that. Please write a code in C programming where there is an infinite code, run it with the help of the Dev C++ software, and you can observe your black screen is continuously printing the data and it is continuously printing unless and until you are forcing the screen to stop with the help of the keyboard, by means of some interrupt. Okay, so I hope that you are understanding my point, relating my point with that. So when Turing machine, so this is very important point to know. Now come to the last point, that is the variations of the Turing machine. What are the variations of the Turing machine? Very briefly I am explaining because I have already explained it. First is multi-track Turing machine. Next one is where there is a multiple k number of tracks is present. I am not going into the details. Then multi-tape Turing machine, then multi-tape, multi-thread Turing machine, then multi-thread Turing machine, then multi-dimensional Turing machine. Next is non-deterministic Turing machine, and another one is there the counter machine. If the counter machine does not have more than 2 counter, then I cannot able to say that it's a counter, it's a Turing machine. Counter machine must have more than 2 counters, then we can consider it as a Turing machine. So there are lots of variation of the Turing machine, but we need to understand one important point, that is what are the important points regarding the variance of the Turing machine. Number one, there are many alternative definition of the Turing machine. Number one is multi-tape Turing machine, multi-track Turing machine, single tape Turing machine, two-way Turing machine, multi-thread Turing machine, single stack Turing machine, there are non-deterministic Turing machine, counter machine, etc. So non-deterministic machines and machines with multiple tapes are there. So these are called variants of the Turing machine's model. But one important point that we must need to remember, this is very very important, that the original model, that means the normal Turing machine, has the same expressive power as they recognize the same class of language. So whatever be the language is recognizable by all the variants of the Turing machine, same kind of language is accepted by all the variants of the Turing machines. So multi-step Turing machine will accept the same language, multi-track Turing machine will also accept the same language, multi-thread Turing machine will accept the same language. So all of them are basically accepting same. So their power is expressive power is same. We will explore some variants and prove their equivalence of the expressive power. So I shall share it with you, so you can able to observe that Turing machines are robust, allowing several variants without affecting its expressive power. You see, in case of the finite automata, how many variants that you have? You have only two variants. Finite automata with output and finite automata without output. With output are basically two types, mealy and more, and without output are basically of two types, deterministic, non-deterministic finite automata. And so there are only four variants. In case of the push down automata, there is only two variants, deterministic, non-deterministic. Okay, deterministic, non-deterministic. In case of the lower bound automata, deterministic, non-deterministic. But in case of the Turing machine, there are lots of variants. That's why Turing machine is so robust, but without affecting its expressive power. This is the very very important point to remember. So I shall share this slide with you, where you can able to find it out. There are how many Turing machines are there, and which are they. There are how many examples of different types of Turing machines. But the important point to remember is that the expressive power of the normal Turing machine or original Turing machine and its variants are basically same. They are not different. Let us take some example, then question, then we shall move to our problem discussion. I am waiting for your questions. Yes, Moina Krok replied, no question, sir. I am waiting for the other students to reply. Moinak Roy replied, Abhishek Ray replied, sir, proceed. Preyoshi Paul replied, no questions. Thank you for your replies. So now we are moving to our problem discussion regarding to all the national examinations. So what are the popular questions? I have gathered 10 questions only. It is if time permits, then I will once again discuss. I can discuss more and more question with you regarding the Turing machine. Okay. First question. Which of the statement is basically false? regarding the halting, regarding the input given input of the Turing machine. As I have discussed, so there are three conditions: Turing machine halts and accept the input, Turing machine halts and reject the input, Turing machine never halts and start looping. Okay, so which is basically, so naturally A, C and D is true and B is false. So my correct proper answer is, my answer is B. So B is false. This is true regarding Turing machine, this is true regarding the Turing machine. So this is basically false. So option B is false. Option B is false. I am discarding it and I am moving it to the diagram, and you are observing that yes, halts and accept the in terms of halting related operations. There are three cases: halt and accept the input, halt and reject the input, never halts or loop. These are the three cases regarding the Turing machine. I hope it is clear to you. Question number 2. Next is finite state machine. Finite state machine is FSM. FSM is a finite state machine. I can say that the finite automata is also a kind of FSM. Now finite automata is, we all know, is recognizable by the regular language generated from the regular grammar. Next is deterministic finite automata. We know that the deterministic finite automata or DFA is basically accepts the regular language, okay, not context sensitive language. Next is non-deterministic finite automata, NDFA or NFA. We already know that the NFA or NDFA is basically going to recognize the regular language. NDFA or NFA is going to recognize the regular language. Okay. Next is linear bound automata. Linear bound automata is going to recognize basically the context sensitive language. Context sensitive language is going to recognize by the linear bound automata. Linear bound automata is going to recognize context sensitive language. We all know that. So linear bounded automata is going to recognize the context sensitive language. We all know that. So our correct answer is context sensitive language can be recognized by D, option D, linear bounded automata. Next, there exists no algorithm for deciding if two Turing machine M1 and M2 accept the same language. Okay. Okay. So suppose I have a language, say A to the power n, B to the power n, where n greater than equal to 1. Okay. So there may be a Turing machine which is accepting this, the finite control unit. Let's say this Turing machine is M1, and there is another type of Turing machine which I have designed. There is various types of Turing machine design is possible. Okay, M2 design, but I can, so L is accepted by M1, L is also accepted by M2, but there is no way to determine whether M1 and this language is accepted by the same two machines, same two, this accepted language, same two machines, or two Turing machines is accepting the same language. There is no way to determine that. Yes, this is a problem which is not solvable, problem. This problem is not solvable using the Turing machine. That's why it is not able to, that's why we cannot able to write any algorithm. That's why we cannot able to implement it with the help of a computer. So this particular statement is true. Next is the problem of determining whether the Turing machine halts on any input is undecidable. I cannot able to say that whether the Turing machine will halt or not on every, there is no particular algorithm is there which will determine that determine the whether the Turing machine will halt on any input, particular input value. Okay, that will depends on the characters present in the string or input. So it is impossible to track. So in case of A, suppose by mistake I have read B. It is computer. After all, it's a machine. It can able to do mistake. We are human being, we are also machine, we can do mistake. So Turing machine is also can do mistake, but when it will do mistake, that is so unpredictable. So that is why it is, this problem is also undecidable. That's why statement number 1 is 1 and statement 2 is 2. Both of them are correct. So our correct answer is option A. Next, which of the following is wrong? Turing machine is the simple mathematical model of general purpose computer. As I said earlier, it is true. Next is, Turing machine is more powerful than finite automata. Obviously Turing machine is more powerful. Finite automata is less than push down automata. Push down automata is less than lower bound automata. Lower bound automata is less than Turing machine. Turing machine has the highest power. No doubt about that. Next is sorry, not wrong. All following is true. So there is a mistake, please correct it. Turing machine can be simulated by a general purpose computer. Turing machine is generated by the general purpose computer. Yes, Turing machine is basically a logical concept and it is implemented by a general purpose computer. Theoretical concept generated by a general purpose computer, that's the correct thing. So all this A, B, C are correct. So all of these are correct. So option D is my correct option. So it is, please correct it, which of the following is true, not wrong. As I said earlier, that a push down automata behaves like a Turing machine when there is a more than 2 stack. Example, say, let me give example. Say W A to the power n, W to the power r, B to the power n. So whenever you are checking W and whether W and W to the power r, whether you are checking with the help of the PDA, you know you need a stack. And whether you, whenever you are checking whether number of A and number of B is equal or not, you need another stack. As simple as that. Otherwise you cannot able to do. So how many minimum number of stacks is required in the PDA to accept this language? Answer is 2. This particular language L is accepted by Turing machine. So I can able to say that if the PDA has 2 stack, then this language can also be accepted by the PDA. Hence my answer is, a push down automata behaves like a Turing machine when the number of auxiliary memory or stack is 2 or more. So correct answer is option D. I think I made myself very, very clear. If you have any kind of doubts, sir, is halting problem of a Turing machine is decidable? Halting problem is Turing machine is not decidable. We cannot decide when a Turing machine halts. We cannot able to decide whether that the Turing machine is halts. For all cases, we cannot able to decide it. That's why it is not decidable. That's why it is not decidable. For all cases, I repeat, for all cases, for some of the cases, I may say that yes, it can halt. But for all cases, it can. For all cases, I cannot say that it is not. It will halt, or it will never halt. Any more question from your side? If the Turing machine has more than two auxiliary, if a PDA has more than 2 auxiliary memory, then it is basically acting just like a Turing machine. I repeat, if a PDA has more than 2 auxiliary memory, it is just acting like a Turing machine. Why? Because W A to the power n, W to the power n, A to B to the power n, this is a language which is accepted by the Turing machine, because Turing machine has an infinite stack. But whenever we are basically try to recognize this particular language with the help of the PDA, we cannot able to do that, because PDA has only 1 stack. With one stack we can check whether w and w to the power r both are basically, we can check w and w to the power r, but we cannot check whether number of a and number of b are same or not. That we cannot check with the help of the one stack. So we need another stack. So there will be two stacks will be needed. So when a PDA has at least two stack, then it will accept this language w a to the power n, w to the power r, b to the power n. I have taken just a raw example. So then it acts as a Turing, basically Turing machine. Let us continue. So same question is appeared in the UGC NET examination 28. There exists no algorithm for deciding if any Turing machine M1 and M2 accept the same language. Please try to find the solution of this problem from the web. And the statement number 2, the problem of determining whether the Turing machine halts on any input is undecidable. This is also true. Please find the solution of this problem in the web. Okay. Single tip Turing machine, multi-tip Turing, multi-dimensional Turing machine, same power. As I said earlier. Okay. Please try to find it out. Please try to find it out. It is said in this particular property of the variance of the Turing machine that original modern and its variants have the same specific power. So I can, from that I can able to conclude that yes, single tip Turing machine is a variant of a Turing machine and multi-dimensional Turing machine is a variant. So both have the same specific power. Multi-tip Turing machine, multi-dimensional Turing machine, both are basically the same. Both are basically same. So there is a correction in the problem. Please correct it. There is a correction in the problem. Both are basically the same expressive power. So this is true. This is also true. Same expressive power. Same expressive power. Same expressive power. But the deterministic push down automata, non-deterministic push down automata, they have different expressive power because all the languages which are accepted by the non-deterministic push down automata may not be accepted by the push down automata. But all the languages which is accepted by the DPDA must be accepted by the non-deterministic push down automata, so their power is different. So our correct option is basically C. Deterministic finite automata, non-deterministic finite automata, their power is same because all the non-deterministic finite all the epsilon NFA can be converted into NFA, and all the NFA will be converted into the DFA, and all the DFA can be converted into the minimized DFA. We have already proved that multiple times we have discussed it over 1 years in due course of time in 2020. So I can say that this power is also same. So our correct option is not option D, it is option B, not it is option C. So we are observing that given a Turing machine, so there are 4 states Q0, Q1, Q2, Q3. So that is nothing but capital Q. There is a capital big sigma, small a and small b is there, and the input stack alphabet gamma, A, B, small b, capital alphabet, and this is basically the Q3 is the final state. Okay, the B is the bank symbol and delta is the function. And delta function, what is that? At a Q0 state, if I give A, I move next state is Q1 and I replace this A by A and move towards right. At Q1 state, if I found B, then I go to Q2 and I replace this B in the stack in the tape by B and move my right head towards right. And at Q2 if I found A, then I go to stay at Q2, I replace it by A and move to the right. And at Q3 if I found B, I go to stay at Q3. Q3 will be in my next state and I replace the stack alphabet B by B and I move my read right head towards right. Now the language M accepted by the Turing machine is given as is basically the option C. As you can see here, it is basically the option C because this is going to be small a. There is a correction. So small a, small b, small a. So look at the small a. So I am starting from Q0 is the initial state. I give small a. So I go to Q1 At Q1 I receive B, then I go to Q2, and at Q2 I go to Q1. At Q1 I receive B, I go to Q2. Yes, right, that's right. And at Q2 I receive another A, so I receive A, I stay at that state. And how many times I can able to stay? Infinite number of times. So that's why a to the power, I need a loop to stay at Q2. So that's why A star, then B. Whenever I found B, then I can move to sorry, there is a mistake. It is Q3. Sorry, very sorry, there is a mistake. If I receive A, then I go to Q3, and at Q3 if I receive sorry, if I receive B, then I can stay at Q3 as many times as I want. Sorry, A star. Okay, very sorry, I have made mistake. At Q0 if I receive infinite number of A, so this is not small b, this is capital B actually. Okay, so at Q2 if I receive capital B, I replace capital B by capital B. I replace this capital B by capital B, and I move my direction towards right, and I reach to the final state, that is the Q3. So again I am repeating. At I have made corrected the mistakes in the problem. At Q0 I receive A, so my string is A, B, A star, B, capital B. That is my string. So first is A. At Q0 I receive A, I move to the next state, that is Q1, and I replace this A in the tape by A. Next, at Q1 I receive B, I move to, at Q1 if I receive B, I move to Q2 and I replace this B by AB in the tape. Now I am at Q2. At Q2 if I receive A, then I stay at Q2 for any number of times. For any number of times I can stay at Q2. Okay, I can stay at Q2, but if I receive B, then automatically I am going to stop my job. I cannot able to reach the, if my input change, if suddenly my input change, I have given B, then naturally you see I am cannot able to reach to my final state, and I am going to I forcefully halt without accepting. Okay, so I stay at Q2 and I replace this A by A, and whenever I read the blank symbol at Q2, okay, and read the blank symbol at Q2, so I can go to Q3 state. I can go to Q3 state where my where I replace this blank symbol by blank symbol itself, and I move the direction towards right. So that's why A, B, A star B, capital B, this is my correct string. So for every non-deterministic Turing machine, there exists an equivalent deterministic Turing machine. Yes, that particular statement we have to check whether this is right or wrong. Second one is, so first of all, we know that a Turing machine is a recognizer. It recognizes the language of a machine that recognizes the language. It is a decider of a language that is a machine that decides the language. Both types of machine halts in accept states the strings that are in the language. A decoder, Turing machine also acts as a decoder. I have already explained in the previous semester also. Act as a decoder. Turing machine act as a recognizer, that means may or may not halt on string that are not in the language on all input. So the a language is Turing decidable if some Turing machine decides, which is known as recursive enumerable language or recursive languages. So the answer is basically, our correct answer is basically C. So only 2 is basically false, because in 2 it says that Turing recognizable language are closed under union and Turing machine languages are closed under union and complementation. So Turing decidable languages are closed under intersection and complementation. Turing recognizable languages are closed under union and intersection. So I can say that always recursive enumerable minus recursive is recursive enumerable languages. So this we come to our second problem, our last problem, that L1 is a recursive language, L2 and L3 be the language that are recursive enumerable but not recursive. Which one of the following statements is necessarily true? L2 minus L1. So L2 is basically recursive enumerable. L2 is L1 is recursive. L2 and L3 be languages that are recursive enumerable. So L2 minus L1. So recursive enumerable minus recursive, that is recursive. So option A, recursive, that is always recursive enumerable. So their basically division is basically same. So answer A is basically which of the following that is basically true. So next is recursive language minus recursive enumerable. So this is absolutely wrong, because the recursive enumerable language is the superset and recursive language is the subset. So it is not always true that the recursive languages minus recursive language is always going to give you the recursive enumerable language. It is not always true. So it is not possible. Next is recursive enumerable language intersection recursive language. This is recursive enumerable. Obviously it is true, because whatever be the language present in the recursive languages, that is must be present in recursive language, because the recursive language is the bigger set and the recursive enumerable language is the superset. Recursive, provided that the recursive enumerable language is accepted by the Turing machine always, but there is no guarantee that the recursive language is always going to be accepted by the Turing machine. There is always a guarantee that it is accepted. Recursive enumerable language is guaranteed. So recursive enumerable languages is the subset of the recursive language. So naturally, whatever recursive enumerable language is recursive enumerable language, this is L2 and its intersection with L1, this is obviously recursive enumerable. This is obviously recursive, because the intersection means common factor between them. And L2 union L1, L2 union L1 is recursive enumerable. Always true recursive enumerable languages are closed under union and union and intersection. That's why recursive enumerable languages are basically recursive enumerable. So that's why A, B, C, D are true, but B is false. So correct answer is B. So in this way we can able to explain our problems in the Turing machines. So we shall continue with in our next class. So thank you all for joining.